Flash memory devices, like memory cards, are a basic and essential tool in filmmaking today, but unfortunately they're also rather complicated. This has led to a lot of confusion and misinformation about exactly how they work and how they can affect your shooting, which unfortunately they can. I have real nuts and bolts experience of developing high-tech products based on flash memory devices, and in this video I'm going to give you a glimpse into how they work, how they can affect your filmmaking, and how to make sure that you don't run into the pitfalls. I think it will be helpful for a lot of video shooters to understand storage media and how they work, at least a little bit. You really shouldn't have to worry about this stuff, but there's a lot more going on inside memory cards than most people realize, and unfortunately this can really affect how they store your video. Even more unfortunately, most memory cards are labelled with information which is so misleading it's basically false, and if you get suckered into believing it, you could find your precious content completely ruined. So I'm going to try to explain what's going on here so that you can understand how these memory cards perform and how to choose cards which will work for the video you're shooting. Unfortunately, this is going to mean delving into the internals of these cards a little, but I'll try to keep it manageable. I'm going to assume, by the way, that you're already familiar with bit rates. If not, my handy bitrate video might help. The basics of memory cards are pretty simple. Whether it's an SD card or CF Express or whatever, a memory card is just a file storage device, just like the hard drive in your computer. It stores whatever files you put on there, organized into folders any way you like. There's absolutely nothing about a memory card that knows anything about video. It just stores whatever files you put on there. In an ideal world, that's all you would need to know, and in fact if performance isn't an issue, that's basically it. But for recording video, and particularly high-end video, the performance of your memory card really matters. Your camera is producing data at a set rate, because that's how video works, and that rate can be very fast. And your memory card absolutely has to be able to capture and store every block of data that's handed to it as it arrives. Otherwise, you're going to be looking at corrupted files or dropped frames. So why is this even a thing? Why can't we just write data to a memory card and have it stored as it arrives? Well, unfortunately, to see why that is, we're going to have to look a little bit about how flash memory actually works. You might imagine that when you write data to a memory card, it just gets electronically written directly to the flash memory. This is how your computer's RAM works. But unfortunately, flash is way more complicated than that. Every memory card contains its own computer, running its own operating system, and it has a lot of work to do. Writing to flash is complicated and slow, still way faster than a spinning hard drive, but much slower than RAM. But because of the way flash memory works, it has to be erased before it can be written. And this erasure only takes place in very large chunks called erase pages. These are typically several megabytes, much larger than the blocks of data that we're writing. And this process is also very slow. Worse than that, repeatedly writing a given location in flash memory will eventually wear it out. To mitigate this, every time you write a block of data to flash, it's written to a different place, which levels the wear out over the entire chip. The good news is that this brings the wear down to a point where you don't have to worry about it. The bad news is that it involves a significant amount of housekeeping by the computer inside the memory card, and that means that the amount of time it takes to write to flash memory depends on what state you catch the card in. For some purposes, you want a memory card to be fast on average, but you don't care how fast it's going from moment to moment. For example, if you're copying bulks of files from a memory card to a PC, you really only care how long the overall copy takes. You don't care if there are occasional pauses in there while it sorts things out. For recording video, this isn't good enough. Your camera is generating video at a fixed rate, and your card needs to be fast enough to catch every single frame all the time, not just once in a while or in bursts with gaps in between. Unfortunately, the numbers printed on the card are worthless for both types of purposes. Not only does it not tell you the minimum safe record speed for the card, it doesn't even tell you the average. Instead, what it's telling you is the absolute best speed that the card can achieve once in a blue moon under the most ideal circumstances. Essentially, the card is guaranteeing that it will never work faster than the speed printed on the front. If that's something that was keeping you awake at night, then I guess that's a relief. But for video, what we want is the exact opposite. We need to know the absolute minimum speed that the card is guaranteed to record at under even the worst circumstances, so that we can be sure that it will capture every frame of video even then. In other words, what we want is the guaranteed minimum sustained write speed. So that's a lot of words to say that you need to get a card that's fast enough for what you're using it for. Which sounds simple enough. Test your card and see how fast it can write data. Unfortunately, it's not even that simple, because how you use or test a card has a huge effect on what kind of speed you will see. Those large erase pages aren't much of a problem when you're writing data to the card sequentially, one block after another, like in a simple file copying test. But suppose you're writing multiple data streams to different parts of the card at the same time, like video and metadata, or video and camera stabilization data, or video and separate audio, like my camera does in slow motion mode, or 360 degrees video, where you're actually recording multiple video streams, or whatever. Whatever the reason, this is a disaster. Every block of data you write would need to go to a different erase page. In principle, this would require an erase for every write, which would be absolutely terrible. In practice, your memory card will work around this as much as it can using a RAM buffer, but the results can still be dreadfully slow. Now, a more expensive card might have a smarter controller and more RAM buffers so that it can shadow multiple areas of the flash memory at one time, and so handle multiple parallel data streams. But here's the thing, how would you tell the difference between the two cards? Both cards will perform identically in a naive file copy test, but in a real-world use case where you might be writing multiple data streams at once, one card might be much slower than the other. This might sound like some kind of hypothetical scare scenario, but actually this is a true story. I hit this issue in a tablet product I was working on. The hardware people were trying to switch to a cheaper memory chip, and suddenly some of our prototypes were running deathly slow, even though the chips were rated and in fact tested at the same speed. I developed new testing criteria and a test app based on writing multiple parallel data streams, and with that app you could see that the cheaper chips were way slower. And we're not talking subtleties here, I mean like 90% slower. The devices with the cheap chip weren't just a bit laggy, they were junk. Even though the cheap chips were just as fast as the expensive ones in a naive test, when it came to a real-world use case, it was night and day. So how you design your testing criteria for flash memory will have an absolutely critical effect on the speed you measure. To cope with this, the SD Association has come up with a system of speed classes, which are designed to measure minimum sustained write speed in real-world use scenarios. The details of the test criteria aren't public, but reading between the lines, the latest V class is specifically designed for video and tests multiple write streams to emulate how a real camera might actually work. The numbers in the class names are in megabytes per second, so you need to multiply by 8 to get your bit rate. The speed classes so far go up to V90, or 90 megabytes per second, which is 720 megabits per second. So what does all this mean to you? Well, if you're shooting video at a higher bitrate or on a more sophisticated camera, I would certainly want to use the relevant V speed class. Check your camera's documentation for what they recommend, or maybe the camera itself will tell you. You can work it out from the bitrate at a pinch. Just remember to divide your bitrate by 8 to get megabytes per second, and that's the number in the V class. There are, of course, other memory cards than SD. The main contender is the Compact Flash, or CF, set of standards. Compact Flash has been around for a long time, but unlike SD, they haven't kept physical compatibility between generations. Instead, Compact Flash has prioritized using the fastest available data bus to give the best possible speed. The latest set of standards for CF is CF Express. I say set of standards because for some reason they've standardized 3 different card sizes. Type A is the smallest with 1 PCI Express lane, Type B is larger with 2 lanes, and Type C has 4 lanes. These cards use the same bus, PCI Express, and storage protocol, NVMe, that PCs use, which should make things simpler and more streamlined. And it's very fast, and NVMe is optimized for flash memory. Bear in mind that CF Express is not compatible with SD. Some cameras have a combo slot which can accept either a CF Express Type A card or an SD card, but internally that's 2 separate slots with 2 separate connectors. As with SD cards, different makes and models of CF cards have different useful write speeds, and as with SD cards, the numbers printed on the card are garbage. For example, this card says 1700 megabytes per second, but it's actually too slow for my R5, which only needs 325 megabytes per second. I think the actual speed is about 300, about a sixth of what they're claiming. So we need to know what speeds the card can actually deliver for video recording. There is a speed rating system for CF cards, and it's called VPG, for Video Performance Guarantee. This sounds good, but unfortunately it seems to be somewhat defunct. The CF Association has removed all mention of it from their public website, and not many recent CF Express cards have a VPG rating. There are a handful that do, so maybe it's not completely dead. Other than that, for CF Express cards, we pretty much have to suck it and see, and at hundreds of pounds for a card, that's an expensive proposition. In the meantime, see if your camera manufacturer gives you a clue. Canon has done quite a good job here. Their support page for the EOS R5, for example, lists which specific cards work for recording 8K RAW. So if you've been using memory cards at all, you're probably already aware that the capacity stated on the card isn't always what you see when you put that card into a camera or a computer. So what's going on? Is this more deceptive marketing? Well, actually, no. There's a couple of issues that cause this, so let me explain. One thing you'll often hear blamed for this is file system overhead. The file system is a complex data structure that manages all of your files and folders and so on within the raw storage of a memory card or disk drive or whatever, and it needs some space for itself, and this is called the file system overhead. However, this generally isn't very significant. The base overhead when the file system is empty might be 0.001%. This goes up as you create more files, as space is needed to manage those files, and the sizes of the files themselves are rounded up to a multiple of the allocation unit size. This wastes some space but makes the file system go faster. That's a classic trade-off you see a lot in computing. We're talking maybe tens of kilobytes per file. If you create lots of small files, that could be a concern, but they would have to be really small files. For the mammoth files we create in video shooting, forget about it. The wastage is going to be a tiny fraction of a percent. Even in stills shooting, where the file sizes are in megabytes, it's pretty insignificant. So why is it that when I bought a 650 GB memory card and put it in my camera, the camera says it's 605 GB? Where did my extra 45 GB go? Well, the issue here is binary-based versus decimal-based units. Of course, numbers are numbers, regardless of what base you state them in, and we're all using decimal anyway. But the issue here is the size of the units. The actual amount of space is the same, but the gigas we're seeing here are different gigas. Whereas most people count things in multiples of 1,000, abbreviated K or kilo, computing people tend to work in multiples of 1,024, because that's a round number in binary. This is sometimes called a binary K, which really doesn't make any sense, but that's what we call it. So traditionally in computing, a kilobyte or kbyte is 1,024 bytes. A megabyte is 1,048,576 bytes, and a gigabyte is 1,073,741,824 bytes, which is 1,024 cubed. In binary, that's a 1 with 30 zeros after it. Nowadays, there are a whole new set of prefixes specifically for the binary-based units. These are Ki, Mi, and Gi, pronounced kibby, mibby, and gibby, which sounds kind of dumb, but at least it's unambiguous. So done correctly, a GB is exactly 1 billion bytes. A GIB is 1,073,000,000, etc., etc. Unfortunately, a lot of computers and devices still incorrectly use the decimal prefixes for the binary-based units. So they'll tell you GB when they should be saying GIB. So technically what they're telling you is wrong, but it's been done this way in computing for a long time. Memory card manufacturers, on the other hand, have an incentive to make their products seem as big as possible. So they tell you the capacities in the standard decimal base units. So when they say a card is 650 GB, it will actually have 650 billion bytes of storage, or just over. A computer or camera, on the other hand, might tell you that the card's capacity is 605 GB, which is actually wrong. It would be correct if they said GIB, meaning gigabytes. Actually, some cameras do it one way and some the other. Even two new Canon cameras that I have do it differently, so they tell me different sizes for the same memory card. So don't be surprised if your camera or your PC tells you that your card's capacity is way less than what it says on the front. And bear in mind that it doesn't really matter. The actual capacity of the card is the same regardless of what units your camera or your PC displays it in. And having card capacities quoted in decimal units, as the card manufacturers do, is actually a good thing, because the video recording bit rates quoted by cameras are usually in the decimal units as well. It's easy to take memory cards for granted. Just plug one into your camera, shoot until it's full, and then unload it onto your PC. And as long as everything works, that's great. But flash memory devices are way more complicated than most people realize. If you one day find that a video you've put a lot of time, money and effort into is corrupted or has missing frames, then life is suddenly going to suck. So if you're shooting high-stakes video, particularly on a high-spec camera, it's worth taking a little time to understand just what your memory card is actually capable of. And since the card manufacturers go out of their way to provide you with completely misleading information, this unfortunately involves a little work on your part. But the information is there, sometimes, if you know what to look for. In any case, I hope this video has helped to illuminate the problems and what you can do to protect yourself from them. And thanks for watching.